Hi, everyone, and welcome to online lecture 16, confidence intervals and the z-test. So last time we did speak about confidence intervals a little bit, right? And we were talking about how they give you a range about which you can be 95% confident that the true population falls in. Okay. So notice how when I talk about confidence intervals, I keep using the word confident. And I don't use the word probability. And there is actually a reason for this. And I want to share this reason for you because this is an important piece about confidence intervals. Okay, so I have this coin in my hand and I will ask you to believe that it is a fair coin with a heads and a tails. And I might ask you, if I were to flip this coin, what would be the probability of my getting a head? All right. And you would probably say 0.5 probability or 50% chance. Great. I agree. Now, let's say I go ahead, and you won't be able to see this property. I'm going to flip the coin, and then I'm going to cover it with my hand. Okay, I flipped the coin. I covered it with my hand. We don't know what this is. So now I ask you the same question. What's the probability of getting a heads? And again, you might say 0.5 or 50%, same as before. This is where statisticians would take a little bit of issue. And they would say, you know what? No, we can no longer talk about probability because the coin's already been flipped. It already exists. The outcome is here. There's no probability about the outcome. The outcome is what it is already. Just because we don't know it does not change that. So there is no probability here. I just looked down and it turned out it was heads. So this is the same with the population mean. Even though we don't know what it is, it does exist in the population. It actually has a value. So that's my point here. So when we're talking about confidence intervals, let's always talk about confidence that the interval contains the true population mean and not about probability. Okay. All right. So having said that, let's return to our calculation for a 95% confidence interval. Here it is again, and I just want to go through it one more time, and then we're going to actually work through an example from start to finish with the confidence interval and some other pieces. Okay. So how do we calculate this? Well, we start at the bottom right with the square root of n. Remember, that's the square root of our sample size. Then we take our sigma and we divide that by the square root of n. Remember, sigma is our standard deviation. So this whole thing together, sigma over the square root of n, remember, is our standard error of the mean. Okay, so we've done our square root, we've done our division. Next step is to do our multiplication. So we'll multiply by 1.96. Remember, that's the number for a 95% confidence interval, because that leaves 2.5% on each side. The number would be different if we were talking about a 99% confidence interval. And those are the only two intervals we'll really talk about. And the number for that would be 2.58. Okay, so we'll only ever talk about 95% confidence intervals, which has the point of 1.96, and the 99, which is 2.58. Okay. So notice this is the same on both the right side and the left side, right? Now, only once we've multiplied do things get different. On the left side, we're going to take our mean, our sample mean, and subtract the value we just got. And on the right side, we're going to take our sample mean and add the value that we just obtained. That will give us the two sides of the confidence interval. Okay. Now let's pull it all together. Let's pull together everything we've been talking about with an example. The post-traumatic checklist, or PCL, has a population mean of 30.12 and a population standard deviation of 15 in a non-traumatized general population sample. Okay. We wish to know if people in the community of Moore, Oklahoma will have significantly different scores on the PCL than a general population sample. So we sample 25 people in Moore, Oklahoma who complete the PCL, and we obtain a sample mean, or X bar, of 36. Okay. So if you've been watching this, you've probably noticed that we have all the information that we might need to start constructing a confidence interval. Now, let's start with the alternative hypothesis, which, if you remember, we pull directly from the actual statement. People in the community of Moore, Oklahoma will have different, that's what it says up here, different PCL scores on average than the general population. Okay. So how do we get to the null? What's the word we add? It's not. Let's do the null. People in the community of Moore, Oklahoma will not have different PCL scores on average than the general population. Okay, so you probably were good with the alternative and null hypotheses, but why am I making such a point about on average? It's because not every single person needs be different. Just on average, we expect those means to be different. Okay. So now we must decide, is this a one-tailed test or a two-tailed test? Remember, we're using the word different here, and that should be our key, that this is indeed a two-tailed test. Had we said higher, lower, it would have been a one-tailed test. Because we did not specify any direction and we just said different, it's a two-tailed test or a non-directional test. Now, notice what I did up here. I brought across all of the information from the problem. This was all given to us. We were given a mu of 30.12. We were given a sigma of 15. We were given a sample size, or n, of 25 and a sample mean, or x bar, of 36. And I find it very helpful when you're doing a little bit longer problems to write out the information that you get out of a word problem. Just write it all out so that you have it at your fingertips, and it just makes it a little bit easier than having to go back into the word problem each time. Okay. Here's our formulas. Remember, we start with the square root of n. So we're starting with the square root of 25, which is 5. Then we're going to take sigma 15 over that 5, and we'll get 3. Okay. So then for our next step, we have 36, which is our x bar. Notice how the 36 we've just plopped in here, minus the 1.96 times the 3, and 36 plus 1.96 times the 3. Again, just to review this one more time, square root of n, square root of 25 is 5. Take 15 over 5, and that's how you got the 3. And it's the same on both sides. Okay. So now we just have to multiply next. 36 minus 5.88 and 36 plus 5.88. That's our multiplication. And then finally, we'll add and subtract to get 30.12 and 41.88. That's our confidence interval. So here's the question for you. Does this confidence interval, 30.12 to 41.88, contain the population mean? Remember, population mean is mu. Here's 30.12. Look, it contains it. It's right at the edge of it, but it contains it. Had our mu been 30.05, it wouldn't have contained it. Had it been 31, sure, it would have contained it. even a little bit more clearly. But here it is, 30.12, right on the edge. All right. So that brings us to an interesting point about confidence intervals. If our confidence interval contains the population mean, we say that our test, our result, falls on the inside, falls in this white portion. And you can kind of see that, right? Here it is. Here's kind of where we fell. Right on the edge here. Right? So, and you can see, let's look back to the problem. This is a bit higher than this, but it's not higher enough. It's not different enough. So when we look here, here's probably where our, right on the edge here is where our 30.12 falls. This would be the population mean going up to 41.88. But because part of it falls, because the population mean falls inside the white part, we're not going to reject. Now, a significance test is kind of easier because with a significance test, we just ask the question, are you on the outside? And that's the question we've been asking as we've been talking about significance tests. Are you on the outside? Yes, reject the null. The confidence interval asks a weird question. It says, am I not on the inside? Am I not on the inside? Well, if I'm not on the inside, where am I? I'm on the outside, so reject the null. See, they're saying the same thing. They're both saying, if you're on the outside, you're going to reject. If you're on the inside, you're not going to reject. They just have a weird way of saying it for confidence intervals. Now, I will share with you that we're not going to continue to work with confidence intervals throughout the remainder of the course. This is pretty much it. We work with confidence intervals for this one Z-type test, and then we let it go. There are confidence intervals for all the other tests we're going to learn about, but we're not going to go into those details, in part because I want you to have the main idea of a confidence interval, but because they are a little more confusing to interpret, I don't want to belabor the issue either. So this is how we approach it. Okay, so confidence interval, am I not on the inside? If yes, I'm on the outside. Now, in this case, when we asked the question, am I not on the inside? We had the answer, no, excuse me. No, you are on the inside. So you don't get to reject. Okay. Now, what we're going to do is we're going to turn to our first inferential test, which is the z-test. And this is basically the same as the confidence interval, except now we're going to ask the question, are you on the outside? Same setup, same numbers, right? I haven't changed a darn thing. Okay. In fact, if you look at this formula, it's very similar. It has all the same components as the confidence interval because they're really the same beast asking the question in different ways. We have an X bar minus a mu, a sample mean minus population mean. Remember this guy? Standard error of the mean. Remember how you define standard error of the mean? Here, sigma over the square root of n. So this sigma x bar equals sigma over the square root of n. And I really want to emphasize that. These two formulas are exactly the same. You can use either one depending on what information you have. So if I was given the standard error of the mean up here, I could use this formula. I was not given the standard error of the mean up here. I don't see sigma x bar. So I must use this formula because I do see sigma and I do see n. Great, I'm set to use this formula, but they're exactly the same. Use one or the other. Okay. So let's start filling in our information. 36 x bar minus 30.12 mu over 15 divided by the square root of 25. Well, we've already played the game on the bottom here. 15 over the square root of 25, remember that? So square root of 25 is 5. 15 divided by 5 is 3. So now we have 36 minus 30.12 over 3, which is 5.88 over 3. If these numbers are seeming similar to the last problem to you, or familiar, that's great. 5.88 over 3 gives you 1.96. Once again, we have to be greater than 1.96 to reject. We have to be in this gray region. We're not. Our mean for our group falls right here, right on the edge. And so we cannot reject. Same conclusion as with the confidence interval. Again, had we gotten 1.97, super, we could have rejected. We'd be in the gray region. Had we gotten 1.90, we'd be further in the white region. But as it is, we're right on the line and we're not inside the gray region, so we do not reject the null. Same conclusion for the matching significance test to our confidence interval. Okay, so we did the confidence interval for a z-test, and then we did the actual z-test. And we got the same conclusion. Okay. All right. So we are now across the road into the land of inferential testing, and this is an exciting moment. Okay. Oops, sorry, I blew past that slide. Didn't mean to do that. So let's talk through the slide. Here's our inferential testing takeaways. We use inferential testing to determine if we believe that we found a significant difference relationship in our sample that would generalize to the corresponding population. This is nothing new. This is what we talked about very early on day 1, day 2, right? That's the difference. Descriptive describes, inferential, we want to draw conclusions about our sample that we want to generalize to our population. Now, the formulas for the sampling distribution of means are going to be used in our inferential test formulas going forward, just like we just used one of those formulas, the standard error of the mean, which will be the most common one we use, in our z-test. And finally, as we've been talking about, confidence intervals and significance tests are highly related. Okay. So let's talk more about the z-test. In fact, let's actually work through another example here. Except this time we are going to change things just a little bit. Now we're going to leave the top part the same. The post-traumatic checklist PCL has a mu of 30.12 and a sigma of 15 in a non-traumatized general population sample. We'll leave that the same, right? We're not changing these numbers at all. The researcher believes that people in Moore, Oklahoma will have significantly different scores on the PCL than the general population. Okay. We sample 25 people, still the same, in Moore, Oklahoma, who complete the PCL, and we obtain a sample mean of 35.52. Not the same. Just change this from 36 to 35.52. Okay. So in fact, this is now closer to this. The 35.52 is closer to the 30.12 than it was before. Remember, before it was 36, right? So it's a little further away from 30.12. Now it's a little closer. Let's see what happens. Here's our alpha of 0.05. Okay. Now our alpha in the last example was 0.05 as well. I didn't specify it, but I will going forward because that's important for you to know. Okay, that's important for you to know. That tells you what the gray regions on that curve look like. Okay. First question, one or two-tailed? What do you think? We use the word different, right? So it's two-tailed. Here's our alternative hypothesis. People in the community from Oklahoma will have different PCL scores on average than the general population. And our null. People in the community from Oklahoma will not have different PCL scores on average than the general population. Okay, pretty much the same as before, right? Okay. Now, suppose the researcher believes that people in Moore, Oklahoma will have significantly higher scores on the PCL than the general population. Now, one or two-tailed. And I hope you're all saying one-tailed, because it is one-tailed. Because we're talking about a direction here, higher. We think they're going to be higher. Okay. Now, our alternative hypothesis is pretty much the same. People in the community of Moore, Oklahoma will have higher PCL scores on average than the general population. All I did really is exchange different for higher. And the null, people in the community of Moore, Oklahoma will not have higher PCL scores on average than the general population. So copied the null from the alternative and just added the word not. Okay. So let's figure it out. Let's do the math. Here's our numbers once again. The only one that's changed is this x bar to 35.52. Here we go again. We've got our z equals x bar minus mu over our standard error of the mean. Once again, I don't see standard error of the mean up here. I don't see sigma x bar. I don't see the symbol up here. Okay, that's okay, because I know standard error of the mean equals sigma over the square root over n. Good. I see sigma, I see n, I see x bar, I see mu. I can work with this. I have all the things I need to fill out this formula. Okay. So I have 35.52 for my x bar, 30.12 for my mu, 15 for my sigma, square root of 25 for my n. Now again, this bottom part is going to come out the same. Square root of 25 is 5. 15 over 5 is 3. 35.52 minus 30.12 is 5.40. So we have 5.40 divided by 3, which gives us 1.80. Okay, great. We have a number. Let's talk about the rounding rule for a minute. How would we apply the rounding rule here? If you said you can't, you're right, because I haven't told you what the original data looks like. I haven't given you any original data. I just have been giving you some summary information, right? I haven't told you what the actual data points look like from the people of Moore, Oklahoma, what their scores on the PCL look like. Okay, but now I will. Original PCL scores were all integers, no decimals. In other words, no numbers beyond the decimal point. That's what that means. What does that mean for you in the rounding rule? Well, if there were no numbers beyond the decimal point, in other words, we had numbers like 36 and 28 and 42 and what have you, no decimals, then our final answer will have one decimal. It'll have one decimal. I see I have two numbers beyond the decimal point here, the 8 and the 0. I only need one, so I'll round to 1, and I will get z equals 1.8. That's the rounding rule. So I know this was an issue for some of you before. I hope this clarifies it further. If you're having an issue with the rounding rule, please feel free to sign up for some office hours so that we can clarify it together. Okay. Okay, so here we are back to the two-tailed test. Remember, we started off by saying that there was a difference in the scores. So looking at the z-scores down here, here's -2, here's -1.96, -1, 0, 1, 1.962. Here's our z's. Where does 1.8 fall? Somewhere right around here, right? Somewhere between 1 and 1.96 is where 1.8 falls. Okay, so we can't reject the null because our cutoff is 1.96. We did not hit it. We're in the white region. We're not in the good gray region where we want to be. We're in this white region, so we do not reject the null. Let's pretend for a minute that this was one-tailed. Remember in the second example, I said that the score would be higher. And again, we have the same setup, -2, -1, 0, +1, +2. But now our cutoff is at 1.64. Now where does 1.8 fall? Well, it falls between 1.64 and 2, somewhere in there, which means it falls in the gray region, which means we're going to reject. So here's my big point. It's super important to know whether we're dealing with a two-tailed test or a one-tailed test. Because as you just saw, same numbers, but when we said things were different, we did not reject. But when we made the claim that the folks in Moore, Oklahoma would have higher scores, we do reject. I have another question for you. What if I had said that the people in Moore, Oklahoma will have lower PCL scores? Lower PCL scores? And I got 1.8 for my answer. Now, the gray region would be down here. This would be white up here. On the right side, it would be all white. On the left side, we would have a gray region starting at -1.64 and heading left. The gray region would be on the left. The right side would be completely white. So if we had a 1.8, where would that fall? In the white region. We would not reject. And that's because of that rule we talked about. When you have a one-tailed test, you have to match the direction of what you claimed. So if I say people are going to have higher scores, they have to have higher scores in order to reject. Even if they have way, way, way lower scores, you can't reject. It's got to match. It's got to match. Okay, and that's a really important take-home concept, one that will carry with us for the rest of the semester. Okay, that is all I have for you guys for today. We are officially over the rickety bridge. We're just going to take tests from this point forward and look at them and tweak them and talk about more tests. So if you were struggling with the last couple of days, please know we're over the rickety bridge and the rest should be a little more straightforward. So be well, take care, and I will talk to you next time.